Okay, so this is the third and last video on our review of exponential and logarithmic functions, as well as solving exponential and logarithmic equations. The two tables that I have here first, the properties of exponents, properties of logarithms, please review those and know them. We are going to start, before we actually look at solving equations, we're going to look at how to use the log properties to simplify. You guys have looked at exponents and exponent properties so many times in so many classes before, but we're going to do a brief review of how to use those log properties because we will be using them for solving. Okay, so in order to simplify log base 5 of 5, remember you're thinking 5 to what power would be equal to 5? Well, that's actually also a property of logarithms, right? That says log base b of b will always be equal to 1, but that's the y, right? B to the first power would be equal to b if you think about using the arrows. Natural log of 1, well, natural log is base e, so you would think e to what power is equal to 1, and that would be 0. And really, it's anytime you're taking the log base anything of 1, that's going to be 0. So that's this first property up here. Anytime you're taking the log, it doesn't matter what the base is, of 1, that's going to be 0, because when you raise, in order to make the base equal to 1, you would have to raise the base to the 0th power. Okay, and then the C, 10 to the log of 2 plus x is actually equal to 2 plus x. Okay, and that is this property that's right below that top one. So if the bases, and remember this is the same as log base 10, right? You don't need to write the base. So if that base is the same, think about rewriting in its equivalent logarithmic form, right? Like that would be the log base 10 of 2 plus x equals to log of 2 plus x. So if those bases match, then you're able to get rid of the log in the base, and it'll just be equal to the argument of the logarithm that's in the exponent position, as long as that argument is greater than 0. Okay, and so same property is applied, but I used base e, so this would end up being equal to 3x minus 4. Okay, and log of 10 to the x squared power actually ends up being equal to x squared. And that would be, just want to make sure I'm referencing the correct, that would be this property up here, okay? And if you thought about writing in the equivalent exponential form for this statement, 10 to the x squared power would be equal to 10 to the x squared. And then the same property is used for f, right? So ln is log base e of e would be equal to the x plus 5 power would be equal to x plus 5. Same property. Okay, and then you should be familiar with change of base formula. It basically says if you want to rewrite or evaluate the log base b of m, that can be rewritten as the log base a of m over the log base a of b, where it actually doesn't matter what a is as long as it's a base that's allowed. But that base just needs to match Now, if you have an older TI-84, you might have to use change of base formula in order to evaluate a logarithm on your calculator, or in order to graph a logarithmic function on your calculator. And if you're using your calculator to evaluate and you're using change of base, you'll oftentimes just want to use like log base 10. So log of m over log of b, or use natural log, since there are buttons, and then you don't have to call anything else up. Or like I said, you might have to if you have an older calculator. So an example would be like if you're trying to find the log base, 4 of 112. That can also be written as log of 112, the argument, over log of 4. Or you could also use natural log. Or you could use log base 2 of 112 over log base 2 of 4, just as long as that base matches. And the reason I am pointing out change of base formula is because we will be using in a derivation of derivatives for logarithmic functions. Okay, before we get to reviewing solving equations, I did want to point out a couple helpful properties. So there's the one-to-one property, which is pretty straightforward. It says if you have b to the x equal to b to the y, that means that x and y, the exponents, have to be equal to each other. Or if you have log base b of x equals to log base b of y, also means that x and y have to be equal to each other. And then the inverse property was one of the properties two of the properties of logarithms that were above, but that's just their name. But as long as you're familiar with the different properties of logarithms, we can use that. So for solving these exponential equations, there are options. So if possible, you could rewrite the right-hand side so that we could use the one-to-one property. Like if you know that 81 is also 3 to the 4th power, you could rewrite the equation and then think, okay, well, by one-to-one property, then x has to be equal to 4. If you didn't know that, or you didn't want to do that extra step, you could just think about rewriting in logarithmic form. You could also think about taking the log base 3 of each side of the equation. I usually like to think of it as rewriting in the equivalent logarithmic form. So that would be log base 3 of 81 is equal to x. So x, and then if I type that into my calculator, x is equal to 4. Okay, same kind of option with the next equation. So if you know that 125 can also be written as 5 cubed, that's great. And then you could say, okay, 7 minus x equals to 3 by the one-to-one property. Finish solving for x. So you get x equals to positive 4. Or you could rewrite in logarithmic form. So that would be log base 5 of 125 equals to 7 minus x. And then finish getting x by itself. So subtract by 7 on each side. Divide by -1 on each side. So that changes the signs on the left-hand side. And then you could type that into your calculator, or you could think about evaluating that logarithm and then simplifying it, and you end up with x equals to 4. Okay. For the next one, we could either use one-to-one property, rewrite the 16 as 1/2 to a power, or we could think about rewriting in logarithmic form, or taking the log base 1/2 of each side and then thinking about applying the logarithmic logarithm properties. So log base 1/2 of 16 equals to 4y, and then dividing by 4 on each side. Okay, so then we would end up with y equals to, and after typing into my calculator, which I didn't have this written in my notes, so I'm going to do this right now. I hit the math button, I scrolled up to log base so that I can just type what I need in. Then divided by 4, we get equals to -1. Y equals to -1. Again, you could have rewritten 16 as 1/2 to a power. Okay, now for solving more complicated exponential equations, and what I kind of mean by that is you don't have the option of using one-to-one property, rewriting and using one-to-one property. You have to think about rewriting in the equivalent logarithmic form or using properties of logarithms. So for the 27 can't be written as 5 to a power easily, right? So then we will think about writing log base 5 of 27 equals to y squared. So y will actually have two values. We would get plus or minus the square root of log base 5 of 27. And that would be the exact value. Well, there would be two values, right? Like you would have the positive and the negative value for y. If you wanted the decimal approximation, you could type it into your calculator, but this would represent the exact solutions, like the exact values of the solutions. No decimal approximation. For the next one, that could be rewritten as log base 4 of 71 equals to 3x plus 2. And then thinking about isolating the x, we would subtract by 2 on each side and divide by 3. So I'm going to do that in a single step. So I would have the log base 4 of 71 minus 2 divided by 3. That would be the exact value for x. You could type into your calculator to get the approximation. And for c, we have 4e to the x squared equals to 64. We actually have to divide by 4 before we can rewrite in logarithmic form. So we would have e to the x squared, and then 64 divided by 4 is 16. So in logarithmic form, that would be ln, right, which is log base e, of 16 equals to x squared. So that would be x equals to plus or minus the square root of ln of 16. So there's two solutions to that equation as well. This would be how we would represent the exact values of those solutions. Okay, and then 10 to the 2x minus 3 power equals to 7. So that would be log base 10, which I can just write as log, of 7 equals to 2x minus 3. And then thinking about adding 3 and dividing by 2. That's our exact value for x. Now, sometimes we have exponential equations that we can think of as being kind of behaving like quadratics for how we solve them. Now, if we have e to the 2x minus 4, e to the x plus 3 equals to 0, you can kind of think of that for, or try and factor it like you would a trinomial quadratic. So just using guess and check, that's going to probably be the fastest. In order to get the e to the 2x, you would have to have e to the x and e to the x. And then thinking of factors of 3, we also have to think about those factors adding up to -4. So I could use -1 and -3. Oops. Right, and just thinking about how those would multiply out to be our original equation on the left side. So then by the zero product property, e to the x equals to 1 or e to the x equals to 3. And then we have to solve each of those equations if possible. So like we would get x equals to 0. I can just solve that one by inspection. And then for e to the x equals to 3, that would be ln of 3 equals to x. Or I could flip that around. Okay, so there's 2 solutions to that equation. Your other option is to do a u substitution. So if you, and that, all that does here is makes your equation look more like a quadratic equation. So replacing all of the e to the x's with u's, we would have u squared minus 4u plus 3 equals to 0. And then just looking at that, maybe that makes more sense to you for factoring. Or like if you use quadratic formula. But you would have to substitute the e to the x back in. So that factors to be u minus 1 times u minus 3. So you would get u equals to 1 or u equals to 3. But then you have to substitute e to the x back in, which then we end up with our same 2 solutions. So either thought process, using a u substitution can sometimes just be helpful visually. Okay. We're going to call these still solving simple logarithmic equations, because when I say simple, it means you usually have the option of using the one-to-one property. Now, this first equation does not have the option of applying the one-to-one property yet, because the right-hand side has a sum of 2 logarithms. But because those logarithms have the same base, we can actually apply the product property for logarithms. And if I go back up here, right, this property right here is our product property for logarithms. So we can think about, because they are the same base, multiplying the arguments. So we can rewrite this as ln of x plus 8 equals to ln of x times x plus 3. Now we have to be careful when we apply the one-to-one property here, because we are dropping the ln's, which makes us an equation that doesn't have the same domain restrictions as the natural log. So we have to check for extraneous solutions. It's kind of like whenever you square both sides of an equation as a strategy for solving, you always have to check for extraneous solutions or solutions that don't make sense. And that's the same thing. My suggestion would be for logarithmic equations, check for extraneous solutions every time. Just make sure that your solution makes sense. Okay, so this ends up being a quadratic. We can think about distributing that x in. So we'd have x plus 8 equals to x squared plus 3x. And we want to get 0 on one side of the equation. Now that's a quadratic that factors nicely to x plus 4x minus 2. So we would get x equals to negative 4 or x equals to 2. But then double checking, well, if we plug negative 4 into our original equation, right, negative 4 would make us take the natural log of negative value here and here. So negative 4 doesn't actually work, and 2 would be our only solution. Right, 2 works if you plug it into the original. Okay, for our next equation, we can't use the one-to-one property, but we could think about rewriting in the equivalent exponential form. 4 to the negative second power is equal to 5 minus 2x. And then 4 to the negative second power, I can write as 1 over 16, thinking exponent properties. And then if we were to subtract by 5 on each side, that would actually end up being negative 79 over 16 equals to negative 2x. And then if I were to divide by negative 2 on each side, which is the same as multiplying by a negative 1/2 on each side, we would get x equals to 79 over 32, which I don't believe simplifies. And you can always think about plugging back in, but for this one, we don't actually, it works, but for this one, because we're not thinking about using that one-to-one property, we actually don't really need to. But it's a good idea to always check your work. Okay, now for this next one in C, we do have the same base here. And we have the logs are being added together, so we can use that product property for logarithms again and rewrite the left-hand side as log base 5 of x times x minus 4. And then because we don't have a log on the right-hand side, we're going to think about rewriting in exponential form. So 5 to the first power equals to x times x minus 4. Okay, that will turn into just a quadratic equation. Now, when we use the product property for logarithms, we did potentially lose, actually, anytime, I shouldn't have said that about the previous one. You should always check. The 79 over 32 does work, but you should always check, because when you're rewriting the logarithmic statement as an exponential statement, you do lose the logarithm domain restrictions. So factoring here, to x minus 5 times x plus 1, the x equals to 5, or x equals to negative 1. But negative 1 does not actually work. So x equals to 5 is our only solution. And sometimes equations can have no solutions too, so you want to make sure you're checking both. Okay, and then we're going to do a few examples of solving some more complicated logarithmic equations. So for this one, you have the option, you can either use the quotient property, for logarithms. Sorry, brain fart. Or we could think about simplifying log base 2 of 2 is just going to be 1, right? So if that turns into 1, we can think about adding 1 to each side of the equation. And then rewriting in exponential form, 2 cubed equals 4x. So that gives us 8 equals 4x. So x equals to 2. And we check that 2 actually makes sense, and it does. Okay, so for the next equation, I'm going to start, since it's ln on a sum of natural logs on the left side, I'm going to rewrite that as ln of x times x minus 2. So that then I can rewrite as e to the 4th equals to x squared minus 2x if I think about multiplying the x and the x minus 2 out. And then this really turns into a quadratic, or e to the 4th. This would, you couldn't factor this. So e to the 4th is our c, is our constant. So we can use quadratic formula to find the solution here. So x equals negative b plus or minus the square root b squared minus 4ac all over 2a. So simplifying that a bit, we would have 2 plus or minus the square root. That would be 4 plus 4e to the 4th over 2. And if we wanted to simplify more, we could think about factoring that 4 out. That's underneath the radical. So that would be 2 plus or minus the square root of 4 times 1 plus e to the 4th. And then that 4, we could simplify the radical. So that would end up being 2 plus or minus 2 root 1 plus e to the 4th over 2. And then thinking about factoring the 2 out, could cancel with the 2 in the denominator. So that actually simplifies to be x equals to 1 plus or minus the square root of 1 plus e to the 4th. And then if you check, the negative actually does not work. So our only solution ends up being x equals to 1 plus the square root of 1 plus e to the 4th, which you could also plug into your calculator to get the decimal approximation. That might be helpful to do for when you're checking your answer. Okay, last example. So on the left-hand side, well, you have options. We can use the why am I having a brain fart? The quotient property on the left-hand side, or we could add log base 7 of x plus 2 to each side of the equation. So you could use the product property and rewrite so that you have a sum of 2 logarithms. I'm going to leave as is and rewrite this as log base 7 of 1 minus x over x plus 2 equals log base 7 of x, which now by the 1-to-1 property, we can drop the log base 7. And then to get the x plus 2 out of the denominator, we have to multiply by x plus 2 on each side of the equation. Take note of domain restrictions, although we'll just check at the end. So 1 minus x equals 2 x squared plus 2x, which is 0 equals x squared plus 3x minus 1. Using quadratic formula, because that does not factor, we would get negative 3 plus or minus the square root of 9 minus 4 times 1 times negative 1 all over 2 times 1. The radical simplifies to be the square root of 13. Okay, and then when you double check for extraneous solutions, the negative doesn't actually work here, or the minus doesn't work. So the only solution to this equation is -3 plus the square root of 13 divided by 2. Okay, so that is our brief review of solving exponential and